Hello everyone, I'm Aparna, a PhD student working with Professor Kaushik Roy at Purdue University. I'm here to give you a brief overview of our work on cross-feature contrastive loss for decentralized deep learning on heterogeneous data. As we all know, increasing the size of the training data set can improve the performance of machine learning models. These days, the training data set size is usually of the millions and billions of data points. On the other side, we have these edge devices that generate huge amount of data on daily basis. Being able to use this data to train our models can help us in improving their performance. However, you cannot simply collect this data at the cloud because of the efficiency and privacy concerns. One potential solution for this is to enable distributed learning, where you accumulate the knowledge extracted from the data rather than the data itself. Distributed learning can be divided into two streams, centralized and decentralized learning. In the centralized setup, you have a parameter server that acts as a master, and all the edge devices are connected to the server. These edge devices compute the gradients on the local data and communicate it with the server, which aggregates these gradients by averaging them and sends it back. The convergence happens at every communication round. These setups are known to have high network bandwidth and a single point of failure. On the other extreme, we have decentralized learning, which completely gets rid of the parameter server and the nodes are connected in a peer-to-peer fashion. Every node communicates the weights with its neighbors, and the convergence happens in linear amount of time with respect to the number of clients. These setups are known to have sparse connectivity and are more generalized because they can also realize a centralized setup. This project focuses on decentralized learning algorithms. Coming to decentralized learning setup, we have a bunch of agents that collaboratively wants to learn a model. They're connected via a sparse graph topology, and the adjacency matrix of this topology is given by W. Every agent has local data that is private and cannot be shared across the neighbors. Each agent also has a copy of model parameters that it updates locally. The updated model parameters are communicated with the neighbors. Note that the communication in this case is synchronous. The traditional decentralized learning algorithms have two major components at every iteration. The first one is stochastic gradient descent, which is local to each node, where every node computes local gradients using the local data and updates the model parameters. The other one is gossip averaging, which is global across the neighborhood, where every agent averages the information received from the neighborhood. Non-IID happens to be a major bottleneck for the practical realizations of decentralized learning. Traditional decentralized learning algorithm has performance degradation with non-IID data. This project aims to close the gap of performance between IID and non-IID datasets in such decentralized learning setups. These are the list of existing decentralized algorithms on heterogeneous data. Some of these algorithms try to modify the local SGD step. Some focus on modifying the gossip, while others also look at momentum updates. In this project, we explore an orthogonal direction of using knowledge distillation approach to handle heterogeneous data in decentralized setups. To do this, we define the concept of cross features. Consider a decentralized learning setup where you have agent I with its local model parameters xi and data di, and let's say agent j is its neighbor. At every iteration, you can compute local features, which are the last hidden layer representations computed on the local model parameters xi with local data di. Any decentralized learning setup has a communication step, which means that agent I receives the neighbor parameters xj. Now we can compute another features or the last hidden layer representations using this received neighbor parameters and the local data. These set of features are known as cross features. We can define two different types of cross features. The first one is called model variant cross features, where every agent uses its local data and computes the last hidden layer representations for each of their neighbors' model parameters, which are received during the communication step. Note that these can be computed locally at each agent. The other set of cross features are known as data variant cross features. These are the last hidden layer representations of the local model parameters xi with respect to the neighbor's datasets. Since you cannot have access to the neighbor's dataset because of the privacy concerns, these cross features are received through an additional communication round. Instead of communicating the data variant cross features for each sample, we compute the mean or averaged feature for each class and communicate this instead. This reduces the communication overhead of the system. Now, in any classification task, every agent locally computes cross entropy loss, which is evaluated on the local data using the local model parameters. We propose to compute an additional loss function known as cross-feature contrastive loss. This includes two different losses. The first one is called model variant contrastive loss, where you compute the L2 distance between the local feature representation and the model variant contrastive loss. So reducing this L2 distance ensures that the neighborhood's model parameters have similar representation for a given data sample. This reduces the model variations caused due to the data heterogeneity. The other loss function is known as data variant contrastive loss, where you reduce the L2 distance between the local features ZII and the averaged data variant cross features for the same class. Reducing this ensures that the neighboring agents have similar representation for a given class. This reduces the disparities caused due to the data heterogeneity across the neighboring agents. Adding these two loss functions on top of cross entropy loss helps us improve the performance of decentralized learning on heterogeneous data. Moving on to the experimental setup, we conduct experiments on various graph topologies, datasets, and model architectures. All the hyperparameters are synchronized across the nodes. The stopping criteria is a fixed number of epochs. The results are averaged over 3 random seeds. The data is partitioned across the agents using Dirichlet distribution, which has a hyperparameter alpha that controls the heterogeneity of the data distribution. Smaller the alpha, larger the heterogeneity. These are the existing algorithms that we compare our proposed method with. Note that the proposed method is orthogonal to all the existing algorithms and can be used in synergy with them. Here are the results for CIFAR 10 dataset on ResNet 20 architecture over a ring topology of 16 and 32 agents. We see an improvement of 0.624% over the current state of the art. We also conduct experiments on various graph topologies and see an improvement of 0.4 to 2.5%. To show the generalizability of the proposed loss function, we conduct experiments on various data sets and show an improvement of 2.5% on an average. To show the scalability, we conduct experiments on larger data sets like ImageNet and show an average improvement of 1.1% over the current state of the art. Additionally, we also analyze the overheads of the proposed loss function. We observe that there is no memory overhead for CCL. Compute overhead comes from the cross-feature computation, which varies from 0.35x to 0.5x. There is a minimal communication overhead as we communicate these additional averaged data variant cross features. Note that the communication and compute overheads depend on the graph size and the type of the graph topology. To conclude, we proposed a cross-feature contrastive loss that helps us in improving the performance of decentralized learning on heterogeneous data. This loss aims to increase the similarity of local feature representations with respect to model and data variant cross features. Our exhaustive experiments show the efficiency, scalability, and generalizability of the proposed method with an averaged performance improvement of 0.5 to 4% over the current state of the art. And in summary, we also show different decentralized learning algorithms with respect to their memory, compute, and communication overhead. This gives a picture of where CCL stands with respect to all the other algorithms in terms of the overheads it introduces. For more details on this project, please attend poster session on day 1. Thank you.